All right, I think we're live. Today I'd like to introduce Alex Levchenko from University of Wisconsin to give our seminar. And his talk will be about hydrodynamics, thermoelectric transport near charge neutrality. And with that, take it away, Alex.
Okay, perfect. Thank you, guys. Yeah, so I prepared for you a couple of slides to. So let me see, how do I move through presentation? Okay, and give me 1 sec. I'll try to do this highlighter for you. Laser. You see the dot, right? All right. So I prepared for you a couple of sort of teasers to introduce the topic first, which are examples from classical physics, but they are, I think, very beautiful examples, and maybe to spark your curiosity a little bit. Then we'll go to some more specific introduction to topics of aerodynamics in the context of electron liquids. And then the bulk of the presentation would be a bit more technical matter. So when I speak about these topics to students, I typically start with this slide. And this slide gives you a screenshot from the Clay Institute of Mathematics, and specifically the page which is devoted to Millennium Problems. You probably know that these problems are give you a grand prize of $1 million if you solve them. And so this problem of Navier-Stokes is currently unsolved, and they say that although Navier-Stokes equations were written down in the 19th century, our understanding of them remains minimal, and the challenge is to take substantial progress towards the mathematical theory which would unlock the secrets hidden in Navier-Stokes equations. So you need to click on this link here for the official problem description, and I wish you best of luck. Now, when you read it, it's sort of very interesting how mathematicians view these topics. I don't think that for physicists, the concept of Navier-Stokes equation would sort of resonate as something fundamental. After all, we understand that these equations are certain approximations for certain things. But a couple of examples that I prepared for you would sort of reinforce this thinking that indeed there are lots of very interesting things that are hidden in them, even at the classical level, that are quite surprising. So in order to stimulate that sort of discussion, so let me show you one fact and then to show you an example. So one thing which is written in all of the textbooks, and one of the first things you sort of see in hydrodynamics is the Stokes formula, and Stokes himself made lots of contributions to hydrodynamics. So he derived an equation for the drag force of an object moving through a viscous fluid, saying that if this velocity of the object v is small enough, then the force is some coefficient, radius of the sphere times the viscosity of the fluid. And sort of fun fact about this formula that sort of transparent, but maybe not so maybe not immediately known to you, is the following. So if we disregard this numerical coefficient for a second, and we'll do a small trick, we will multiply this equation by extra power of viscosity. So we have viscosity squared over viscosity, and then we multiply and divide by the mass density of the fluid. Then we will be able to form this dimensionless coefficient A, which is a typical size of the object. For the sphere would be radius, V rho over eta, and this should resemble to you Reynolds number, and then will be ratio of viscosity squared over the mass density. And so the nice feature of this formula is that if you'd like to drag an object through a viscous fluid, any object of any size, but you'd like to drag it in such a way as the Reynolds number is 1, then the force that you need to apply is sort of universal and is a property of the fluid itself. So it's just the viscosity squared over the mass density. And for water, it is 10 to the power minus 14. So it means that, let's say, dragging a big ship or dragging a tiny piece through water would require the same force as long as you drag it at Reynolds number 1. All right, so other thing that is a bit more curious is the so-called Scaleup Theorem. You can find a very beautiful discussion of this thing in a very famous article by Purcell, which is published in the American Journal of Physics. If you haven't seen this article, I strongly advise. It's really fun reading, almost like a bedtime story, but it's really beautiful and filled of stories and ideas. And so he talks about the following. he talks about life at extremely low Reynolds numbers, when in the Navier-Stokes equation, that is just sort of a Newtonian equation of motion for the fluid. If we have an extremely viscous regime, inertia term is not relevant. Convective term, which is non-linear in velocity, is also not relevant. Everything is governed by the high viscosity. And there is the Scaleup theorem that says that if there is an object that tries to swim through extremely viscous environment having only 1 degree of freedom. So let's say in this case for the scallop, this will be an angle of opening. And let's say the scallop would like to open its shell and close that shell to do this reciprocal motion in order to swim. So the statement is that this will not be possible. So let me show you an actual experiment of that. And so this is a fish in a container. And so I got this slide from Grisha Falkovich, and kind of appreciate it for sharing this. So let me try. So I need to undo the laser pointed and try to run the video for you. So you need to pay attention right now to the head of this fish. This fish would open the mouth and will try to swallow one of these food pieces floating around, and then it will close its mouth and see what happens. So I'll run it a couple of times. So it opens the mouth, a little piece goes inside, it closes the mouth, and it escapes. Let's do it again. Opens, closes. Okay, so this fish was fooled. So the water in this container was made purposely more viscous than the normal environment to this fish, and so it does a normal thing for it when it tries to eat, but it doesn't work. And so this is kind of an example of this sorry, I'll just repeat example of this Scaleup theorem, that by just simply repeating the motion you could not swim, and this fish unfortunately couldn't figure out how to solve Navier-Stokes equation. Now in his article, Purcell discusses that in order to swim you actually need at bare minimum 2 degrees of freedom, and he discusses this really beautiful example of the swimmer doing certain cycles. So let's say we have a swimmer with some initial position with, let's say, arms up, and we do a sort of cycle by changing angles in such a way that we return at the end of the cycle to the same position. Then in parameter space of these angles, we form a loop, a closed cycle, and can be proven that the displacement of the swimmer would be proportional to the area enclosed in the cycle. And that sort of starts to resonate with things like Berry phases and some adiabatic invariants and so on. And that's all true, and it's all a very beautiful connection. And I, at this point, just simply make reference to beautiful work of Wilczek and Shafir and Avron, Kenneth and Gott, who showed that swimming in highly viscous environment by just simply changing the shape of the swimmer is actually connected to non-abelian gauge theory and so on. So, I mean, indeed, there are sort of extremely beautiful examples in the Navier-Stokes, even in the most sort of trivial and you would say boring regime of extremely viscous flow, but yet there are these jewelers that you could find, and this I just leave for you to enjoy and maybe do some extra reading when you have some spare time. So now coming to a topic of today's presentation about electronic hydrodynamics. So next few slides are introduction, and this is very, very condensed introduction of the research that took place about 60 years. So I'll cover many decades, but I'll do it very quickly, and I will introduce sort of more most important topic for us, which is called the Guruji effect. I will talk about what it is and how this Guruji effect kind of manifests in more modern examples of electronic hydrodynamics in graphene or other strongly correlated fluids. So first of all, why it is sort of unusual to even think about hydrodynamics in application to electron liquids. So typically, when we think about electronic transport in solid state, we think of electrons scattering of impurities, electron scattering of phonons, electron scattering of other possible excitations. We sort of intuitively think this to be a highly quantum mechanical problem. And the picture of viscous flow, like water flows through the pipe, is not sort of a picture that first comes to our mind. Nevertheless, there are regimes then this picture is actually possible. And this is the regime when the length scale of momentum conserving electron-electron collisions becomes the shortest length scale in the problem. So when we think about a flow of, I don't know, oceans or coffee in a cup, we are not interested about the length scales of intermolecular scattering. We are looking at the much macroscopic scales. And so as long as we can ensure that electronic equilibration occurs at the time scales and length scales that are small enough compared to other scales at which electrons lose their momentum and energy, then these generic hydrodynamic descriptions could be applicable. And the power of hydrodynamics is that it naturally describes most fluids, regardless of the strength of interaction and some other details, but it requires as an input parameter just a small set of input variables, and these variables would be thermodynamic quantities that describe the state of the fluid, and then also some kinetic coefficients such as viscosities. So I would say that the field of electronic hydrodynamics was pioneered by Guruji in early 60s. He worked in Kharkov Physical Technical Institute at that time, and then he spent his professional career at the Low Temperature Institute in Kharkiv. I used to live 2 trolleybus stops from the institute, and I'm kind of intimately connected to this place. This place has been in the news for unfortunate and sad reasons quite a lot these days, but so all of the work on electronic hydrodynamics by Guruji and his group was done back in Ukraine and Kharkov. So he derived an equation of motion for electron liquids in a metal that looks like very much as an Navier-Stokes equation. He started, however, from much more microscopic description. He started from quantum kinetic equation for electrons and phonons subject to some disorder scattering. But he made this assumption that I described to you in the previous slide, that electrons scatter of themselves much more efficiently than they scatter phonons and etc. So he assumed the existence of slow conserved variables, and he projected kinetic equations into the slow modes. In this case, slow mode would be just a hydrodynamic velocity of the fluid, and he arrived at the end of the day much simplified description. So there are electric field driving forces, and the balancing forces of viscous stresses. Nu here is a kinematic viscosity. Kinematic viscosity would be shear viscosity divided by mass density, and then some term that describes the pure relaxation of electrons scattered of impurities. And then this equation should be supplemented by the constituent relation connecting the particle current or electrical current to hydrodynamic velocity u. Now, in the regime when viscosity is irrelevant for some reason, let's say very efficient.
Sorry, Alex, do you mind if I ask you a question right now?
Yes, yes.
So you mentioned that the scattering time of impurities should be much longer than the electron-electron scattering time.
That's right.
Where is this in this equation? Can we see anywhere in this formulation?
In this equation, not, but it should be appeared in much earlier level when you start with kinetic equation. And the mere fact that you have a hydrodynamic mode. So in order to arrive at this equation, you sort of need to consider the flow of the liquid in a reference frame that is flow. So you need to apply a boost or Galilean transformation. So you say that, let's say, energy dispersion would be something times P times U. And this is where you would assume that you have slow modes and proceed with this sort of projection procedure. So you need a slow varying variables on certain time scales. So at this level, it is not present, but it is present in much earlier level of the kinetic theory.
Well, but you will have it very soon on your right bottom, picture. You have LEE.
That's right. Correct. I will come to that just in a second.
Okay. Yeah. Thank you.
So here I just want to say, sort of to connect the two regimes. One is more standard sort of regime, kinetic regime, that if viscosity is irrelevant, we see that hydrodynamic, this macroscopic velocity is just proportional to relaxation time. This gives us current proportional to electric field. And so this is ohmic regime that is governed by the Drude conductivity. However, if we are in the opposite regime, when there is no relaxation in the bulk of the flow and everything occurring due to the viscous stresses, of course, then we need to answer the question where the relaxation of momentum occurs, because electron-electron collisions conserve momentum, unless we talk about the clubs that are not in this picture either. So then we need to think about the flow in a finite size geometry. So let's say in a quantum wire of certain size or in a whole bar of certain width, W, then momentum occurs at the boundaries, and there is a momentum outflux due to viscous stresses occurring at the boundaries. And so then this flow realizes sort of an analog of this Poiseuille flow, and we can derive, and what Guruji did, derive this formula for conductance in this regime, when conductance scales quadratically with the width of this channel, and then is inversely proportional to the viscosity of the fluid. Now, to what Ilya was asking me, is that if you forget about the driving force, meaning the left-hand side of this equation, and just concentrate on the right-hand side, we can see that this combination of the two terms introduces an intrinsic length scale in the problem. So indeed, kinematic viscosity times Laplacian by dimensional units is kinematic viscosity divided by some length scale squared times u. And this second term is u divided by tau. So comparing the two, we see that there is intrinsic length scale xi that is, roughly speaking, kinematic viscosity divided by tau, or multiplied by tau, excuse me, in taking the square root of this expression, which can be massaged into the geometrical mean between electron momentum relaxing electron impurity scattering and momentum conserving electron scattering, which is inside of the kinematic viscosity. And this object is called a Guruji lens. And this Guruji lens, it covers the crossover between the bulk flow. So meaning that if the width of this channel is much bigger than LG, then you are sort of back to the ohmic regime. Or if the width of the channel is smaller than LG, you are back into the Stokes-dominated regime of electronic hydrodynamics. Now, if you invert conductivity and you write resistivity, then you will see that resistivity would be proportional to viscosity, like in the Stokes formula. And so Guruji predicted himself that if this regime is realized, it should manifest itself with the negative differential resistance. So it should be a regime of temperatures where you try to increase, well, you increase the temperature, but resistance goes down. Now, if you think about this from the mindset of sort of a conventional thinking about electronic transport, this is highly counterintuitive, because we think of resistance as sort of a measure of scattering. We increase temperature, we increase probability of scattering of electrons, scattering of anything possible, phonons, and so on. So resistance should go up. But again, the whole spirit here is that you shouldn't think like this. You should think about this collective behavior of electron fluids. And I should remind you that in Fermi liquids, and I will elaborate in the next slide, that viscosity is inversely proportional to the square of temperature. So you increase temperature, viscosity goes down, resistance goes down. So that is an essence of the Guruji effect. From the point of view of classical physics, I think this regime is very intuitive, and we experience this every day when we cook. So if we pour oil in a frying pan and we heat up the oil, it becomes more fluid-like. So resistivity, this drag, goes down because the fluid viscosity decreases with an increase of temperature. So pay attention, this is 63. He wrote a review article that was published in the Physics Uspekhi, which is Russian review journal, about the same time. And I would say that was it. And then next, I would say big development was in 1994, because it took that much time sort of to get into the regime that this becomes reality, rather than sort of theoretical desire to get into materials that are pure enough and tunable enough that you can realize it. And this experiment from Lawrence Malenkov is considered to be like a first hint into the electronic hydrodynamics. It is not really a linear response measurement. So he was using current to inject into the quantum wires into decks to locally heat electrons by Joule heating, and he measured differential nonlinear resistance, and he thought about the current as effectively being effective electronic temperature, as I said, through the Joule heating mechanism. But he saw this downturn in resistances and attributed this as a manifestation of the hydrodynamic behavior, as you can see even at the title of the paper itself. Again, I would say that the field was quiet for quite some time. Even after that, I couldn't find much of the discussion of electronic hydrodynamics, really. And I would say the next milestone sort of appeared with the discovery of very clean high mobility 2DEX and graphene. And so here I collected few representative plots of now linear resistance measurements of a variety of 2D systems as a function of temperature. So some of these plots I took from a very beautiful and nice review by Boris Spivak, Sergei Kravchenko, Steve Kivels, and Huang Gao on strongly correlated to these electron and hole systems. So as you can see, these are holes. So this upper plot are holes in gallium arsenide quantum wells, exhibiting this behavior of non-monotonic temperature dependence of resistance. And in that study, which is also co-authored by Huang Gao, the statement is that they believe that this is intrinsic electronic effect, because if you try to think about phonon contribution, it's out of the picture. Also pay attention to the scale of temperature. These are in the range of small temperature regime. You of course can ask me how this could be attributed to electronic hydrodynamics that sort of is higher temperature regime. We need to ensure that electron mean free path is small, but I need to remind you that in regime of very low densities, Fermi energy itself could be as small as 1 Kelvin or 10 Kelvin. So even though by actual numbers, it looks like very low temperature thing, you always need to compare it to an actual Fermi energy in the systems. And for these systems, they're also highly correlated. Typical RS parameter, which measures the strength of electron interactions, would be somewhere in the range of 10 to 30 to even 40. So some of the systems are the onset of the Wigner crystallization in 2D, so they're highly correlated. So 2D holes in silicon MOSFET, 2D holes in p-doped silicon germanium. And this plot here in the lower right side, I took from sort of first experiment from Pablo on magic angle twisted bilayer graphene. This transport measurement was done in a normal state just above this onset of all of this cascade of phase transition of superconducting and insulating behavior. This is normal state measurement. In the panels represent the density of 2D system. This is zero field measurement as a function of temperature. And again, you see this upturn, downturn, and upturn monotonic behavior, which is having this downturn slope reminiscent of the earlier proposal of Guruji, saying that perhaps this is should be attributed to a collective viscous behavior of electron liquids. So my goal is maybe not so much to convince you that this is exactly the case, but I will try to give you hopefully plausible and convincing argument that maybe this is indeed the case. And so let me try to do that. So I will do that first by giving you an example from 1D physics. It's just much easier to try to give you this convincing argument, but this can be generalized to 2D, and I will continue to elaborate in the next slides on this. So imagine that we will consider a flow of electrons, strongly interacting electrons in 1D channel. Let's assume that for kind of realistic also discussion that this 1D channel electron liquid is subject to a long range inhomogeneity potential, not short range impurities, but long range of potential due to, let's say, doping layer or some uneven screening that creates profile of up and down of local value of electrochemical potential. So let's consider the flow. So what would be macroscopic description of such fluid? So we need to ensure continuity equation, and I will consider only steady state properties. And then the Navier-Stokes, steady state Navier-Stokes in the linear response would be simply a balance of the viscous stresses and external driving. This pressure term by general thermodynamic arguments can be written as the density times gradient of the local chemical potential times entropy and gradient of temperature. And the chemical potential and electric field can be driven into general EMF. So we will consider a response of the system to external electric field. Now, the continuity equation tells us that the current, which is given by velocity times particle density, is constant. So we need to ensure that the gradient is zero. Nevertheless, density and current individually can be, of course, coordinate dependent, depending on the cross section when I stand in this wire. Now, then I take this velocity and bring into the stress tensor. In 1D, there is no shear. There is only a bulk flow. So stress tensor will be just the bulk viscosity times the divergence of this velocity field. So the stress tensor would be given by bulk viscosity, current, and gradient of inverse density. And then knowing the stress, I can calculate with the help of 6 volume of Landau, Lifshitz, and fluid dynamics, I can calculate entropy production in this viscous flow, which is the average of the viscous stress with basically the gradients of the velocity, which roughly speaking just square of this expression. So I will get current squared, viscosity, and then averaged over the space, gradient of inverse density. And then I can compare this to the Joule heating in the flow, and this gives me already a resistance. So this part will give me a resistance, which is of viscous origin, but entropy production is also possible due to heat fluxes, and I need to do the same type exercise with the second equation for the entropy current. And believe me that similar line of considerations will give you a second contribution to resistance that would be inversely proportional to thermal conductivity. So in 1D, resistance is conductance quantum, temperature divided by thermal conductivity, multiplied by entropy per particle squared. And then second term is bulk viscosity times the gradient of inverse density squared. Now in 2D, there will be a factor of 2 here in the overall prefactor, and the second term, which is viscous term, should be generalized. You need to add additive contribution from the shear viscosity here. Now, the power of the prediction of this formula is that nowhere in this derivation we said anything about the strength of interactions or being perturbative in nature of sort of, which is hinted in all of the, let's say, Boltzmann calculations. All details of interparticle interactions are hidden in these quantities, meaning the thermal conductivity, viscosity, equation of state, which is in this case is given by entropy, density, and so on. So of course, we could not reliably calculate them in a strongly correlated fluid, but generality and power of hydrodynamics is that if they are given to you, let's say from the measurement, then you can use them to make predictions for other quantities, in this case for resistance. So let's try to analyze this.
Sorry, Alex, so quick question. So the angular brackets, what's the averaging?
Averaging over the space. So it's highlighted here. So it's
non-uniform due to this potential, right?
Correct. Yes.
Okay.
Yeah. So I just tried to make it a little more realistic for actual samples, and I will show you that STM data in 2D graphene, of course, shows that the system is non-homogeneous, and so this would actually lead us to new hydrodynamic features that I will discuss maybe in 15 minutes from now. So now what I'd like to do is, as a sort of a poor theorist, try to distill certain predictions from this formula for some states that we know, and at least qualitatively. So let's analyze this formula for a 2D case. Let's try to do that. And I will do this for a Fermi liquid regime, where we will take some Fermi liquid expressions for thermal conductivity and viscosities in 2D case. So I will go now to 2D example. The formula is the same, as I said, up to some small modifications. In order to consider a concrete disorder model, I will assume that there is a doping layer underneath of electron system. This doping layer creates a screened Coulomb potential, D here would be distance from the doping layer to a 2-deck system. And we will do this averaging. So I could translate special average to momentum space, reciprocal Fourier space, and do this averaging in Q. So in Fermi liquids, we know what the thermal conductivity is from seminal work of Abrikosov and Khalatnikov and generalizations to 2D. So up to some logs and factors and so on. So thermal conductivity is Fermi energy squared over temperature. Shear viscosity is Fermi energy squared times divided by T squared and times particle density. So now we need to ask ourselves, what is the regime of applicability of this formula? And remember, I told you that we need to ensure that electron mean 3 paths should be smallest scale on the problem. What is the scale here? We need to ensure that it is smaller than the scale of the momentum loss. And momentum loss would be momentum outflux due to this disorder potential. In this case, it's characterized by the sort of correlation radius, which is D itself. So we need to ensure that L of T, here I forgot to put electron, smaller than D. So electron is inversely proportional to T squared in Fermi liquids. So it means that we need to be in the regime of temperatures higher than E Fermi divided by this parameter in the problem, which is square root of K Fermi D. For typical devices that I looked at in all days in the strongly correlated regime, K Fermi D is somewhere in the regime from 4 to about 30. So depending on density and depending on D. So it is a parameter. I mean, it's not a very big parameter, but it's sort of an okay parameter for theory purposes. So this condition defines scale T1, which I call an onset of hydrodynamic behavior. So it means that I could not pretend to use this formula in the low temperature regime, but I could use it in a higher temperature regime. And for this reason, in the plot, I only highlight temperatures which are higher than T1. Now, what is scale T2? Scale T2 is the following scale. So if I take my formula from the previous slide, this piece, thermal conductivity, and this piece with viscosity, and then I use these estimates for thermal conductivity and viscosity, I would get these two terms here in the formula in the red box. And then I can ask myself at which temperature they become comparable to each other. So this happens to be at this temperature T2. Okay, and then T2 happens to be higher than T1. So it means that the interplay of these two terms, so thermal conductivity growth as a function of temperature while viscosity decreases, give you initial down term of resistance at this onset when you enter into hydrodynamic regime, but then this thermal conductivity term overcomes, and so you would get this growth of resistance. So I would say it's at least qualitatively consistent with the data that I was trying to tell you. So if you would allow me to tell that a hype of this peak is sort of the onset of hydrodynamic regime in each of the plots, this downturn and upturn is sort of qualitatively captured by this formula, macroscopic formula of resistance through thermal conduction and viscous effects. And another sort of predictive power is that we can compare the value of the resistance at the peak and the value of the resistance at the minimum. And so at least for these models, we can say by how much resistance should drop and try to compare this to experimental data points. And at least in those examples for strongly correlated states, it is not far. I mean, the numbers work so that they are sort of in the right ballpark regime. So here I just simply like to tell you that, okay, you could think about this transport data in these hydrodynamic terms and perhaps provides a new understanding and a new way to interpret the data. And you can continue this. The third term of this formula is an extension of this flow in the magnetic field. And it's possible to show that magnetic resistance would be inversely proportional to the fluid viscosity. And perhaps magnetic resistance is the way to measure fluid viscosity of electron liquids in the solid state system. Okay, and I will come back to that also a little later for magnetotransport properties in this talk. All right, so we have an array of highly mobile and very pure 2D electron systems ranging from graphene and some other exfoliated 2D materials in the family of transitional metal decalcogenites. We have super high mobility clean gallium arsenides, two-dimensional electron systems, both electron-like and Hall-like. We have delassophites, ruthenides, and perhaps some other systems. And the question we can ask is, what is or are the most fundamental manifestations of the strongly interacting electron flows? And you can ask these questions for any of the systems, and there is a literature for any literature examples. I will focus on graphene, and I will give you 3 examples of these manifestations, which I think are quite unique and quite interesting, and most importantly are sort of well under the control theoretically and been tested experimentally. So this work has been done in collaboration, the theory work, I should say, been done in collaboration with my postdoc, Sonchi Lee, with my long-term collaborator, University of Washington, Anton Andreev, Maxim Hores from the Hebrew University of Jerusalem, and my local colleague here, Victor Brar at UW-Madison. And I will also highlight experimental work of other groups, primarily Manchester group and the group of Philip Kim, Harvard, from doing all kinds of measurements. So I will focus on thermoelectric effects in graphene. I'll talk about the Guruji effect in point contacts and narrow channels. And I will speak about, time permitting, about non-local and vertical effects at the very viscous regime, though, both for electrical and thermal measurements or scenarios. So I would say the first sort of experimental breakthrough, I'm not pretending here to talk about the historical who was first to discuss. I sort of arranged in a way that it is more convenient for me to talk about these topics. So first I'd like to talk about the beautiful experiment by Philip and his group and collaborators and theory colleagues about the giant violation of the Wiedemann-Franz and breakdown of the Lorentz ratio in graphene, what they termed the Dirac liquid. Again, Dirac making a reference to linear dispersion of quasi-particles in graphene. So fluids, electron fluids in graphene do not possess Galilean invariance like usual Navier-Stokes. And as we discussed, this creates very important nuances that alter transport properties. So a reminder, Lorentz ratio is the ratio of thermal conductivity to the product of electrical conductivity and temperature. In sort of this Drude version, a single particle picture, this is believed to be a number, which is pi squared over k Boltzmann over E squared. And this is a Lorentz ratio, a Lorentz number L naught, which will be our reference point. So I should say that in general grounds, we should expect that in graphene close to charge neutrality, meaning when we tune total density close to the Dirac point, we should expect a very dramatic difference between the heat flow and electronic flow. And this decoupling of charge and heat currents would create this anomalous thermoelectric effects. And so next, I would say 5 to 7 slides is to explore this physics. So what's been seen experimentally is that we need to concentrate on this panel D in this plot, that the blue line is the thermal conductance line as derived or as expected from this formula. And the dotted points are the experimentally measured quantities. And it is also important to see that the domain of temperatures where these things shows up is actually sort of not the low temperature regime, but rather higher temperature regime, a domain of temperature between somewhere 50 to 100 Kelvin. And this plot, which is at the bottom of the page, is a sort of a phase diagram in temperature versus density now, where it shows this giant enhancement of the Lorentz number as compared to the conventional value where this anomaly occurs. So it is sort of in the regime close to charge neutrality. And if you take a cut in temperature domain somewhere in the higher temperature, again, this is important to ensure that electron-electron mean free path is shorter than anything else that exists in this system. Now, again, as a reminder that Wiedemann-Franz is not sort of an artifact of a bad theory. Actually, it works really well and surprisingly well, I would say, for a number of simple metals and systems. And you can see this as a function of electrical conductivity through several orders of magnitude for aluminum and copper and some other gold and so on, some simple systems, and also through several decades change of the carrier concentration. Again, all of the systems are labeled here, and the cut line is the bare value of the Drude value prediction. So it's not something sort of very unique. It is seen experimentally in many systems. So deviations of that is quite interesting on its own. All right. So let's go and see what kind of Guruji picture of hydrodynamic electron flow should be modified in applications to graphene devices. And this is kind of a slide that introduces main changes and main notations that I will use. So electrical current in the Guruji picture is given by hydrodynamic mode. It's just electron charge times particle density and hydrodynamic fluid velocity. And this is what it would be for a Galilean invariant fluid. But electrons in graphene are not. And they also have what is called an intrinsic conductivity. So even when particle density is 0, the electrical current is not. Again, calculating the intrinsic conductivity is sort of a serious work. But again, in some perturbative Boltzmann-like approaches, calculations are being done. And it's quantity of the order of quantum of conductance times some logs of temperature, which are cut off of your theory. Another modification is the existence of the intrinsic thermoelectric coefficient. So it means that if the system is biased also electrically, there is gamma present here. And similarly, we need to make modifications to entropic current, which is given by the entropy density times the hydrodynamic velocity, thermal conductivity, and this intrinsic thermoelectric coefficient. So for Galilean invariant fluids, if we want to get back to Guruji picture, we need to send sigma and gamma to 0 in this formula. So this would be modifications to the constituent relations. Now, if we consider the flow in the whole bar geometry and we do a projection of the sort of generalized Navier-Stokes equation to the geometry, it would actually look very much like in Guruji case. We'll have a shear viscosity times the gradients of u. So I consider a flow in x direction. So there is only x component of the hydrodynamic velocity, which depends only on the y component of the in this coordinate system, so across the channel. And so the driving forces that would be EMF and gradient of temperature, it is convenient for me would be to write them in the form of this dotted product between particle density multiplying the electric field and accompanying entropy density multiplying the thermal gradient field. So if we solve this equation in the whole bar geometry with non-slip boundary conditions, so meaning sticking boundary conditions of the fluid at the edges of this mesoscopic sample, we would recover that velocity field has this famous parabolic Poiseuille-like profile. Then we can calculate the average current in the system that consists of sort of hydrodynamic mode. So this quantity which is directly proportional to u would be my hydrodynamic mode, and relative mode, meaning relative mode due to intrinsic transport coefficient, and relative I make a reference to relative to the stationary fluid. So we can calculate currents, and these currents are linearly proportional to forces, and these are then coefficients of this matrix. So J here is the column current of electrical currents, and entropic currents will give you the entire matrix of thermoelectric coefficient. So we can calculate it. So let's look at this matrix. So electrical resistivity would be given by inverse intrinsic conductivity and the piece that depends on the width of the channel D. I'm sorry, I somehow switched notation. So I introduced here, I know D. So D is the width of this channel. So this is that. We can calculate an intrinsic thermoelectric coefficient, and then we can calculate the effective thermal conductivity. So what I would like to tell you that in this mesoscopic whole bar devices, the actual measured quantities in transport measurement are not intrinsic one. So resistivity, as you can see, it depends on fluid viscosity. Thermal conductivity depends on everything. It depends on intrinsic thermoelectric coefficient, viscosity, intrinsic conductivity, and so on. So the most remarkable property of the thermal conductivity is actually happening in the regime of charge neutrality. So close to charge neutrality, where particle density is much smaller than entropy density, and we can take it even exact charge neutrality. At exact charge neutrality, conductivity is just intrinsic one. It is independent of viscous effect. Nevertheless, thermal conductivity would be still strongly viscous dependent. So this term will be absent and this term will be absent, but we'll have a strong dependence through entropy density. And this what exactly gives rise to this appearance of enormous enhancement of the Lorentz ratio, meaning that electrical resistance is fixed, but thermal conductivity is big. And in fact, the most also interesting that for wide enough channels, if you're measuring D, this term, which is this effective thermal conductivity, can overcome intrinsic value. So here I plot for you effective Lorentz number in units of E squared and Boltzmann constant, which shows this giant peak appearing, and we sort of can quantify this peak and go as high as an order of magnitude high. And by the width of this peak, this width is controlled by intrinsic conductivity in units of conductance quantum and multiplied by the fluid viscosity and the width of the channel. So again, measuring how width changes with temperature or the size of the mesoscopic device gives you an access to the measurement of the fluid viscosity. So of course, graphene are not perfectly clean and homogeneous. STM data shows that the systems, even in boron encapsulated form, still is susceptible to different inhomogeneities, which is called this regime of charge puddles. So up and down sort of lakes of electron hole-like regimes. They are quantified by the intrinsic length scale, which is experimentally somewhere in the range from 10 to 100 nanometers. This is an intrinsic length scale of long-range disorder. And so the description for perfectly clean whole bar can be generalized to this flow itself. I should say that this disorder could not be treated like a point-like disorder. You need to develop also hydrodynamic treatment of this disorder scattering, which we did. It's sort of rather technical for me to go into it, but I will highlight two key signatures that signature physical effect. First of all, this disorder induces an intrinsic friction. However, unlike the regime of point-like disorder that Guruji himself considered, an effective friction coefficient can be written down as local variations of density, particle density, and entropy density squared averaged over the system, patches larger than psi, and actually can be expressed through entire matrix of thermoelectric coefficients. As you can see, this denominator here is quite complex. It means that this friction coefficient is extremely strongly dependent on particle density and temperature, and in general, it's very difficult to calculate it. So it's one thing. Second thing is that various quantities that enter these formulas, macroscopic hydrodynamic formulas, are renormalized by this disorder. And the most non-trivial renormalization occurs to intrinsic conductivity itself. It is renormalized by viscous effects and can be written down as sort of average of density fluctuations divided by viscosity. I would say that this is highly non-trivial. The disorder, please pay attention of a plus sign here. So disorder in this case enhances conduction, and this is again, sort of counterintuitive from the point of view of usual transport. Disorder actually obstructs conduction, but here this collective effects enhance conductivity. And I will give you yet another example when this happens, when we will consider flow in narrow constrictions. So we can generalize this to the regime of Guruji crossover and consider crossover from flow in a bulk to flow in the whole bars. And so we did that. So we calculated the macroscopic matrix of thermoelectric coefficients, not just in a restricted geometry, but in the bulk of the flow. So there is this prediction for electrical conductivity that consists of intrinsic conductivity, this disorder enhanced effects, finite doping effects, and then enhancement of the thermal conductivity, and so on. So we calculate that. I could say that another interesting feature that in the bulk, one should expect appearance of the vortical component of the flow that perhaps could be observed by scanning probes. Observations of current vortices thus far been elusive, but I hopefully will comment on that closer to the end of the flow. Very recently, just about a month ago, sort of a breakthrough experimentally been demonstrated, and so current vortical effects are being seen in some of the samples. Okay, so that's the same comparison that, but for a bulk regime. This is theory for the Lorentz ratio. This is experiment from Philip. This would be Mott formula, and this would be also compared to the Phillips experiment. And again, so we expect to see this enhanced and anomalous thermoelectric effect. So I would like to very quickly tell you about similar things in the Corbino geometry. It may sound like a very minor change doing just a geometrical change to the problem, but it leads to quite dramatic and fascinating effects. So basically, if you consider a Corbino disk, meaning that inner electrode and outer electrode and the flow in the circular geometry, and here I will discuss only zero magnetic field case. Okay, so Corbino, of course, devices are used for measurements of magnetic resistance, but I will need just circular geometry for certain purposes. Now, circular geometry enforces certain things which are connected to continuity of electric and entropic currents. It means that they must decay as 1 over R. So the first formula here are expression for the current continuity in the circular geometry. Okay. So it means that without, so this, remember, X here is particle and entropy density, and capital X are conjugated thermodynamic quantities. So it means that these 2x2 equations can be solved to find U and X. So I do know already at the level of the continuity equation how hydrodynamic velocity varies as a function of coordinate in the system. And this should already puzzle you a little bit because, I mean, the continuity itself dictates what the hydrodynamic velocity is, even before we started solving Navier-Stokes. This is not the way it appeared in the whole bar geometry when we had to solve Navier-Stokes in order to determine what the distribution of the velocity would be. So then you're sort of puzzled a little bit for a second and say, well, okay, if I already know what my distribution of potential is in the distribution of hydrodynamic velocities, so what Navier-Stokes tells me, and then to your amusement, you would discover that if you take 1 over the R solution into the projected radial component of the Navier-Stokes equation and the cylindrical coordinates, you will discover immediately that the left-hand side that give you viscous stresses, this operator in the radial coordinates, applied to a function which is 1 over R, give you 0. Okay, it vanishes exactly, which leads you with sort of stunning, I would say, observation that the force density in the bulk of the flow, so anywhere in between, so inside of the fluid, is identically 0. So it means that local electric fields and temperature gradients arrange themselves in such a ways to expel force acted upon the fluid. So then if there are no forces, but there are fluxes, you're sort of worried, what does it really mean? And because these are mutually exclusive sort of statements. And what really happens is that in order to accommodate for this mutually enforcing sort of conditions, you need to think about local drops, discontinuous drops in the electrical potential and thermal temperature applied to the device across the device. Okay, and there can be actually measured. They are reminiscent to sort of Kapitsa boundary effects, but they are completely different, in fact, because in the Kapitsa boundary resistance, which occurs in systems with mismatched, highly mismatched thermoacoustic impedances, here the amount of jump is determined by viscous property of the fluid in the bulk of the Corbino device. So in particular, the size of the jumps can be related to viscosity of the fluids. So we can calculate resistances here as well and calculate them again to determine the entire matrix of thermoelectric coefficients. And we can also quantify these jumps through the viscous stress tensor and sort of macroscopic tensor. So I could just maybe make a reference to this work that we've done with Anton and Sonchi if you're curious about this, but to tell you that these are not artifacts, I would like to show you a recent experiment from the group of Shahalalani and his collaborators in Weizmann and Manchester, who actually measured distribution of the profile exactly in Corbino disk. This is really amazing experimental work. They fight it very hard with all kinds of other effects because their devices are not perfect. There are contact resistances, there are resistances in the bulk, there are viscous contributions, but if you sort of in the kinetic regime sort that out, subtract all of the resistances that are not of the hydrodynamic nature, this is what you would get. This red line here shows you a complete expulsion of the forces from the bulk of the flow. As you can see, it appears only in the temperature regime, which is a higher temperature regime where you expect to see hydrodynamic behavior, and also resistivity as a function of temperature in this inset shows the signature of the Guruji effect, meaning this non-monotonic temperature dependence. So at least you've done your due diligence, you've checked all of the possible things, and so this sort of reassures that these are not just some artifacts of our bad approximations, but probably real physical effects. This can be extended to magneto field effects. So I kind of calculated magneto resistance, but this is topic on its own because magnetohydrodynamics for this non-Galilean electron liquids is quite interesting, and maybe someday I'll talk about this as a sort of a separate topic. Very quickly, another beautiful manifestation of this effects are the flow through the narrow constrictions. This was an experiment by Andres Geim group where they saw an enhancement of conductance through so these square patches are patches of whole bar graphenes that are connected to each other through a constriction. This constriction is essentially kind of macroscopic quantum point contact, and the conductance through this constriction, as you can see in this plot, varies quadratically with the width of the channel, and this should remind you this Guruji initial prediction, and that's also a manifestation of the viscous effects. So this is an experiment, and I think the theory for that at first was worked out by Leonid Levitov and Grisha Falkovich, and then others looked at that from different perspectives. My colleague Victor Brar measured similar things in sort of different configurations, creating macroscopic defects in the bulk of the flow with electrostatic gating, and also see an enhancement of this conductance once temperature is raised from the kinetic low temperature regime to high temperature regime. So this beautiful scaling. So this is second example. And again, yeah, so this is the reference to original work of Levitov and Falkovich, showing you ballistic regime that according to Landauer scales linearly with the weights. Viscous regime scales quadratically with the width of the channel. By the way, this manifestly breaks Matthiessen rule and the kinetic regime, and Matthiessen rule tells us that we need just additively add resistances. Here we actually additively adding conductances, which means that these resistances are added in parallel to each other than in series. So hydrodynamic regime offers quite interesting things that kind of breaks normal dogmas of solid state transport. Okay, I'll skip that. So there are imaging, both different imaging techniques with NV sensing and with STM and so on, trying to actually visualize the actual distribution of the profile of electronic velocity in these mesoscopic samples. They are a bit more difficult to, I would say, interpret, but there are many groups that see in this Poiseuille-like flows and non-Poiseuille-like flows. So I would say that this field is flourishing. And I will conclude in last minute about this beautiful prediction of existence of vortices. Again, initially by Falkovich and Levitov, that this viscous effect should create you a highly non-local response. And if you try to source drain the voltage across the device, you ultimately will discover that there will be a current vortex developed. And if you put another pair of contacts away from the source drain, you will discover yourself that the current would be flowing in the opposite direction to what you were sort of injecting. This would give you negative non-local resistances. In some other cross-section, you would discover vanishing resistance. We sort of looked at this as a function of density with my student. Let me skip to that. There is very big difference between electrical bias and thermal bias. And I think that these distinctions also make it possible to measure these vertical flows not only in the electrical domain, but also in thermal domain. So meaning through imaging of heat distribution across the sample. So unfortunately, this vortice has been elusive. Nobody saw them up until very recently. And so you could scratch your head and say, well, could it be explained differently? And I would like to quote Van Gogh. He wrote a letter to his brother, and he said something which I believe truly sort of applied to physics thinking. So he says that two things that remain eternally true and complement each other, in my view, are: do not snuff out your inspiration and power of imagination. Don't become the slave of the model. And on the other, take the model and study it, for otherwise your inspiration won't take in material form. And I think it's very true in physics that we need models, even simplified models, to sort of understand something, but we don't need to be bound to these models to try to be creative and trying to think, create new things and go beyond these models. And I think this very last experiment from Elis Zeldov group is just that. I mean, they really tried to force liquids and induce different regimes. So they created this very tricky devices with apertures, so that there are some part of the current that could sneak into the circular objects, and you sort of force a fluid into the circular trajectory. And then by fine-tuning of density and temperature, and very clever, I mean, this experiment is really outstanding. I think that they provided us first glimpses of appearances of the vertical flow trapped in the circular objects, and they analyzed stability of the vertical flow and so on. So I would expect that this field of hydrodynamics will continue to evolve, not only in applications to graphene, but to strange metals, highly correlated metals, and non-Fermi liquids, and so on. I think it is very powerful. And that's the end of my talk. So thank you so much. And as always, I'm very happy to take questions.
Thank you very much. It was a very good talk. So yeah, with that, I open the floor to questions. Is there any questions from our audience here?
So Alex, I have one more question. You mentioned already something which you didn't have time to talk about, the viscous flows in the presence of a magnetic field, I guess, right? Yes. So do you think it might be relevant or interesting even to the case of a strong magnetic field, like quantizing field or quantum Hall regime or anything like that?
The topics that being discussed is, of course, this connection from semi-classical regime of small fields in the context of Hall viscosity to a quantized Hall viscosity in the high field regime. So the short answer, at least to maybe understand this question, it is very interesting. Indeed, I would say to you that even in the regime of small fields, there are plenty of highly non-trivial responses that appear, both in thermal Hall and just usual Hall effects that are sort of unique to these systems. What could happen in high field is even at the moment beyond my comprehension, I would say. So I'm sure the answer is yes, but I'm still busy figuring out even small fields limit.
All right, thanks.
All right. I think that should be it. If there are no other questions, I'd like to thank you very much, Alex, for that wonderful talk. Yeah.
Yep. Thank you, guys. Yep. Thank you.
Bye.
Yep. See ya.